Well, these look like it's on bakery and culture. What do you forget? I love it. I get that. Or like, they seem to go right to the definitely one. I don't know. But like, I was training my content one day. That's what, yeah. Well, now
It's like 5 ago, you put spinach. Not with potato, you don't, not like, but my grandma makes it with like. Like, I'm not saying it's what works. And then like different shapes, like there's the garden.
If you want to do it.
All right, today we're going to talk about comparison tests. The idea here is that sometimes we may have a series that looks like it could be some variation of geometric series test or p-series test, but it doesn't quite fit. Something is a little bit off, so it doesn't quite fit into the test. But the idea with comparison test is that we use a more simple series that we know the convergence behavior, whether it's diverging or converging, and then we use that simple series to determine whether something more complicated is either also going to converge or also going to diverge. There'll be guys copy down notes as I walk through some of it. Let's say that we have A sub n or two different series or two different rules of sequence. You have A sub n and B sub n, and we know that A sub n is less than or equal to B sub n. We know that relationship to begin with. And the idea here is that if my B sub n converges, then anything less than B sub n must also converge. But the flip side doesn't necessarily stand. If B sub n converges, or sorry, so if, let's say A sub n converges, then we don't know for sure that B sub n can converge. So if something smaller is converging, we don't know if something larger than that will also converge. I mean, it's kind of like this gray area, right? I mean, we know this will converge, but anything bigger, it may or may not converge, but it's not a very it's not a very strong argument. Right? Now, the other side is if the smaller function or the smaller series diverges, then we know that the larger series must also diverge. Direct comparison test is a test that we use to determine convergence for more complex series by comparing them with simpler series. So let's say between two series, let's say the larger series diverges. Then we can't say that the smaller series is going to diverge as well, because it could diverge, but it could also converge. We don't know where that line is. So comparison with direct comparison test, it's a little clunky. It's not, this is kind of like the integral test in the sense that it's almost like, you know, we're going to exhaust all of our options before we have to, before we would want to deal with direct comparison test. It's not going to be the first one that we go to. It's almost like a last resort, like, okay, nothing else works, fine, we'll do direct comparison test, see if that will get us to the answer, or fine, we'll do integral test. But typically this is the least used test because it's we typically can find something that's faster and easier than this one, but we'll still need to practice through it. So let's look at number one after you guys had a chance to copy that down. Okay.
Okay, determine the following series converge or diverge 1/3 plus 2 to the n. Now, this in itself doesn't quite fit into any series that we can recognize. I mean, if we were to do anything, we typically should do the nth term test first. But the nth term would be inconclusive because this series would, the sequence would go to 0, so inconclusive for nth term. But what we can see is that this does resemble a p-series, right? So what if we compare with 1/2 to the n? What do you know about 1/2 to the n? I'm sorry, this is not p-series. This is going to be what? Geometric series, right? So this is the same thing as 1/2 to the n. All right, what do you know about this series? This is going to converge, right? So we know that this series will converge. So let's see what that relationship is. So if I have a converging series, what is the relationship with this one here? Is this going to be smaller or larger than 1/2 to the n? It's going to be smaller, right? Because the more I increase the denominator, the smaller the value gets. So we know that this is true, right? We know that 1/3 plus 2 to the n is less than 1/2 to the n. So by direct comparison test,
I just put ECT.
yeah, DCT is fine. Mhm.
Sorry, does that say sine?
Oh, sorry, since. Let's finish spelling the word out. By direct comparison test, since 1/2 to the n converges by geometric series test, 1/3 plus 2 to the n will also converge. All right, second one here, 1/4 to the n minus 3. This in itself, that minus 3 kind of messes things up a little bit, so it doesn't quite fit into the test that we can recognize by itself, but we can find something that is kind of the parent version of it. We can look at that 1/4 to the n. And this is also what? Geometric series, right? Converge or diverge? Diverge, okay. Now, what about this one here? What's the relationship with this? This is what? Larger or smaller than this? Larger, right? My denominator is getting smaller, so my denominator is getting smaller. My overall value is getting larger. So here's the relationship. So there's an issue here because we know that this converges, right? But anything larger than this line, it's kind of like a gray area, right? I mean, it could converge, but it's not a very strong argument, right? We know that it's probably going to converge, but it's not a very strong argument. So we can say that this is inconclusive as it stands. Does that make sense? No, not enough either. I think by nth term test, this is still going to head towards 0 because that minus 3 is not going to do anything.
But
Hmm?
1/0 is undefined though.
1 over infinity is basically 0.
Oh.
Right? Infinity, right? So this is inconclusive. However, what we can do is we can compare with one over 3 to the n, right? We know 1 to the 3 to the n. This will converge. And now we have a better relationship here, right? We can say for certain that 1 over 4 to the n minus 3 is definitely smaller than 1 over 3 to the n. Right? This denominator is definitely larger than this one, which makes it smaller. So this one, we can say that, okay, we know that this series will converge. Yes.
Are you able to compare it to 1 over 3n? If like 3 doesn't have an n.
Right. So we know that as far as geometric series goes, we know that 1 over 3 to the n is definitely less than 1 over 4 to the n. Right? We kind of have this relationship in front of us. Wait, I'm sorry. Greater, right? Greater. Denominator is smaller, so the overall value is greater. So if we know this relationship, then we know that a minus 3 is not going to have much impact. So we're kind of looking outside the box a little bit and finding something that we can use. Yeah.
So even though that it's just their limits that are in that order, do not necessarily at every n would make that true. You can still write that inequality. Like if you were to plug in like 1, then that would be true. So you can.
Well, we know that all these cases are when n is approaching infinity.
Okay, so you can just assume that.
Yes. Yeah. I know it's a little clunky here. It's like, prefer to have something that's a little bit more defined, but this is how direct comparison can be used. Yeah. Right. Because we're basically trying to find, there are other tests that could potentially handle this. But right now, if we're only using direct comparison test, it's inconclusive, but we're really trying to find something that can be a better fit. Yeah. Mhm. Yeah. So, okay, I'm going to say that as far as our tests go, if you see a series, whether they're asking about converging or diverging, the answer is never going to be inconclusive, right? The problems are always designed in a way where we can always come to a conclusive converging or diverging. Okay. And when all is said and done, this is going to be a last resort, right? So basically, if we're at the stage where we're using direct comparison tests, it's because we've exhausted all the other options. And if we're exhausted all the options, we kind of think outside the box a little bit to figure out, okay, I can't do inconclusive. Is there a better series for me to test? Because looking at this, I can almost say for certain this is going to converge, right? Because that minus 3 is not going to have much impact. This is going to converge. We're just trying to find a good comparison so that our argument can be more rock solid. Does that make sense? Yeah. So I know that this is not going to be our preferred test. This is usually reserved for complicated series where we just can't find any headway with any other test. And we use direct comparison as a kind of like as a last resort because it just doesn't fit nicely with other tests.
So integral test would work for that problem, right, too?
I don't think so because integral test with U substitution, we're not able to quite find the U value that fits.
Oh.
Yeah. So I think when we do integral tests, we typically want to look to see, okay, can we see U substitution fulfilling and making headway, right? So if so integral test kind of has a certain look to it. It kind of looks like something that U substitution can handle. If not, then we want to look at other tests. All right, number 3. 1/7 n squared plus 4. This doesn't fit exactly into a series, but if we kind of strip away those things around it, this is basically coming from which family here? This is related to, yeah, 1/n squared, right? And what do you know about 1/n squared? Yeah, it's a P series that converges. All right, so this is if we want to compare with something that is converging, that means we want to prove converging. So if we want to prove convergence, we want this to be the larger value, right? Because we know that everything underneath it, smaller than that, we can guarantee will converge if the larger series converges. So what's our relationship with this one here? Is this larger or smaller? Smaller, right? So this one is a good fit for a direct comparison test. Or we can make a strong argument with the direct comparison test. Because we have a smaller series compared with a larger converging series.
You need it to be 1 in the numerator compared to just a constant.
Yes. Yeah. Okay, the next one is limit comparison test. This one will be used more often, and this has a certain look to it. If you have rational functions, limit comparison test is a good fit for that. So let's go over what that does. It says that if I have two series, okay, and it's similar to direct comparison test in the sense that we're still looking for a simpler version of the series that we know the convergence or divergence for, but the process is going to be a little cleaner. The idea is that if I once I identify that simpler series with the new series, I'm going to divide them. Now, whether I divide one over the other, whether it's A over B or B over A, it doesn't really matter. So the order that you divide them is not going to matter. The important thing is that we're going to take the limit as n approaches infinity and see what we get in return. Okay. If we get a real number, that means our limit is finite and positive, then we can say for certain that both these series will share the same converging or diverging property. So if the simpler series that we're testing against is converging and the result of this limit gives us a real number, that means limit comparison test is something that we can use, and we can say that both series will either converge or diverge. Okay. If it goes to infinity, then that means that this is not a good test. That means we want to find a better test. It's not going to be one that that we want to use. Likewise, if the simpler series diverges, and if we do limit of one over the other as n approaches infinity, and it gives us a real number, then we know that both series will diverge. Okay, that the one that we're testing will share the same behavior as the simpler one that we know the convergence divergence for. Okay, let me show you some examples of that. Okay, so limit comparison test is a good fit for these types of problems. It has a certain look to it. Basically, it's a rational function that kind of has, these setups here. If I have a bunch of terms in the numerator, a bunch of terms in the denominator, and it kind of has that rational form, they're all raised to n raised to a certain power. This is usually a good fit for limit comparison test. So the idea is that we want to find a simpler version to partner this with. Well, first thing, we should do nth term tests, right? But nth term tests will be inconclusive because the limit of this does go to 0. So we're kind of stuck. So what we want to do is we want to reduce the numerator and denominator at least the highest degree to find a comparison partner. So if I were to strip away, if I was just focus my attention on just the highest degrees, n squared and n cubed, what's the difference between them? It's if I were to cancel out the n's to get n's in numerator and denominator, I'm just left with a difference of what? 1 over n to the third power, right? So whatever the difference is, that's going to be a good comparison partner for us to deal with here. So I know that 2n squared over 5n cubed. I'm going to strip away the coefficients as well. I just want to find the simplest difference relationship between the two of them. Okay, so my comparison partner is going to be 1 over n cubed. That's going to be a good comparison partner. Now, what do you know about the series here? This converges by what? B series, right? So if I can get the limit of one over the other to equal a real number, then I know that this series must also share the same behavior as this series we're comparing with. Okay. So limit as n approaches infinity. It really doesn't matter which one we divide by. We can do this divided by this, or the new divided by the complicated divided by the simpler. I'm just gonna. I think I'm just always going to do the complicated divided by the simpler. So if I'm dividing this, that's the same thing as this multiplied by what? The reciprocal of this, right? So. But right now, I'm just going to show what we're really doing, really dividing one by the other, which is going to allow us to just bring it up and do a multiplication out of it. Okay, so if I multiply this through here, and if we're doing limit as it approaches infinity, we only care about the highest degree, right? So I get 2n to the 5th minus 2n cubed. I don't really care about that 2n cubed. Okay, is this going to lead us to a real number? Yes. Yes, my degrees match. My coefficient is a real number. 2/5 is a real number. It is a finite number. Therefore, we know that this is a conclusive test. Therefore, we can say by limit comparison test, since 1 over n cubed converges, this series also converge.
The test, like or the quiz, do I have to like put justification or? Since,
No, you can just, how about this? Yeah, you can just say series converges by LCT, right? I see your work. You do need to identify what your conclusion is with the simpler series. But after that, that's fine. You can just say series converge by LCT, limit comparison test. Okay, this one feels more structured, right? It just, once you find that simpler test, you're always dividing by each other, and then it's not as all over the place as direct comparison test. But there's a certain look to it, right? There's a certain type of problem where we should be able to look at a problem and say, okay, this looks like a good fit for limit comparison test, right? And if you can identify a good fit for limit comparison test, then typically we're always going to get something that's conclusive because we already know that it's probably going to work out. Okay, number 5. What's a good comparison partner for this? Yeah. What do you know about 1 over n squared? Converges by, yeah. Okay, so try that. You can take this, divide it by the, or multiply by the reciprocal, and limit as n approaches infinity, and see if that reaches a real number. If it reaches a real number, then we know that this series, that these two series must share the same behavior. Right, limit equals to 1/5 if you do the complex divided by the simpler one. Or if you got the if you divide it the other way, you'll get 5 over 1. That still works, right? That's still a real number. So it doesn't matter which one you divide. As long as you divide one by the other, we'll get the same result. Yeah.
You get your comparison partner of 1 over n squared. Can you just say that your original one is always going to be less than 1 over n squared and stop there by the last one?
Yeah, that's true. You can also use direct comparison tests. Yeah. But I think for most students are going to treat direct comparison tests as a last resort. It just feels cleaner. I think most students prefer the comparison test. But yeah, there's going to be some problems where there's multiple paths to the solution. And sometimes it's kind of up to you to see which one you want to use. But there are some problems that you're forced into one test because none of the other tests works. But if there are multiple paths to the solution, then identifying any one of them would earn you full credit. All right, let's try number 6. Okay, what's a good comparison partner for number 6? Yeah, 1 over root n. We know about 1 over root n. That diverges by p series because p is less than 1, right? Good. So if we can get the limit of the expression of the ratio to produce a real number, then we know that both of these will share the same divergent behavior. Number 6, the comparison test is conclusive for this one. So because the simpler series diverges, we know the one that we're testing also diverges. All right, try number 7.
Sure.
Yeah.
Why would it be 1/3? Because on the bottom, the coefficient to n is.
Oh, sorry. You're right. It's 1 over square root of 3. Thank you. Thanks. Try number 7. 7 should be pretty straightforward as well. I will walk through 8 and 9 with you. So. All right, everybody good with 6 and 7? Okay, let's look at number 8 here. N times 3 to the n over 4n cubed plus 2. If we want to find a comparison partner, Let's take the most important things that are sticking out here and divide them. What can I strip that all the way down to here? Three to the n over, yeah, we can even drop the 4 over what? N squared. Okay, what do you know about this one? So this is what? Nth term, right? Nth term can help us show what is going to happen with this one. So we can say this diverges by nth term.
When I think let's look at the initial fraction here, do it term, right? Still.
Yeah, but it doesn't feel as strong as going through this test. I know, I mean,
That's an exponential at the top.
that's true. That's true. This is exponential times n over, yeah. So I guess nth term can actually get us there. Yeah, you're right. Nth term can get us there. For practice purposes, though, let's go through comparison test. As a reminder, logs, if we're doing direct comparison, or if we're doing comparative growth rates, logs grow slowest, followed by radicals, followed by polynomial, followed by exponential. So in this case, exponential is over my polynomial, so therefore the numerator is growing at a faster rate. This is going to infinity. Okay. But if we take this and we divide it by our comparison partner, then we can get a real number, and that real number will also tell us the series diverge. Okay, one last one here, number 9. What's a good comparison partner for number 9? Yeah, because I have n up top, n to the 3 halves below. If I subtract those two, or if I cancel everything out, I have 1 over, the leftover is 1 over n to the 1/2. And what do you know about 1 over n to the 1/2? Divergence. Okay, so there's your comparison partner. And if we can get a real number out of this process, we know that this series must also diverge as well. Okay, so for homework, you're gonna finish up the AP practice that we didn't get to the day before. So page 25 to 35. I'll send out a reminder on Sunday. Yeah.
I got stuff.
What are you?
I don't for a lot.
So
Mine is money.
I can't compare diversion when it comes with a conversion, right? It's gotta be either conversion and conversion or diversion and diversion. And it's gotta be in the same, it's gotta be in the right relationship. If I'm comparing with a diversion, the one that I'm comparing with has to be larger in order for me to call that also diversion.
No, they just push it, or I don't have the information, they won't like.
I said it's like.
Also, like the base of the video. I read that here.
No.
No.